Now the next question is, why logistic regression? Like, are there any problem areas where applying linear regression is bad? If yes, what are those exact problems? So we'll see them in the next few slides. So what if we want to predict the categories instead of a real number? That means our target variable y is no longer a continuous variable. It could be binary, ordinal, or categorical variable. So essentially we are talking about the classification problems. So all of these problems are of classification type. For example, exam result prediction, pass or fail, the binary outcome. Image classification. So given an image, identify which animal it is. Right? It's a multi-class classification problem. Similarly, others are also. So let's understand this through an example. So in our previous toy dataset, we have added one more column, which is a binary variable. The column name is past, and the description of the other columns remains similar except the marks. So this hours of study denotes the average number of hours a student studied throughout the year, and this time marks denotes the marks obtained by the student in the previous year, and the past variable denotes whether the student passed this year or not. So essentially, if you just look at this record, so what we are saying is that a student studied for 12 hours on an average throughout the year. He obtained 91 marks previous year, and this time he passed or she passed. Right? That's a description of the record. And now, since we have three columns, it would be difficult to visualize. Hence, we'll be dropping off the marks wala column, and we'll be working only on these two columns, hours of study and the past. Okay. So we have a classification problem here, where basis the hours of study, we want to predict whether the student passed or not. Right? So it's a clear classification problem. So can we fit a linear regression model here? Just think about for a minute. So yes, we can definitely fit a linear regression model here, something like this, right? But the next point would be that this is a real line, and we want a binary variable here. We want to predict the classes 0 or 1, right? So for that, maybe we can take a threshold somewhere here. Let's say at 0.5, and can draw a line here, something like this here, and any value which is above this 0.5, we can classify it into class 1, and for values below 0.5, we can classify into class 0, right? So that means somewhere this would be the decimal boundary. So all the points, so if we just go by this logic, all of these points would be misclassified, right? Including this one, and all of these points would be correctly classified. This is misclassification. These would also be correctly classified, right? So it's a bad classifier, but we have got a classifier by using linear regression model. All right. Now someone can argue that this can be the better line than the previous one, because all the green points and red points are on the uh, other sides of this line. So anything above would be in class 1, anything below would be in class 0, right? But this doesn't make sense at all, because essentially you are predicting the same value for each of the x values. For example, if you take, let's say, 6, the prediction would be somewhere here, same 0.5 for 8, for 10, for anything, right? So essentially you are not even classifying at all. So for this line, the slope value would be 0, right? And s theta x essentially will turn out to be a simple theta naught, which is this. So this is a useless model. So although we have fit a linear regression model on a classification problem, but there are two major problems with this approach. The first problem is that this output from this model can be anything, right? Because it's a straight line on the real space, so it can give you any value, right? If you can extend this hours of a study up to any value, and it can give you any value on the y-axis. So the output is not limited, right? For example, this. But what we expect our model to return either the binary output, or let's say multinomial output in case of multi-class classification problem, or this output should be in a fixed range. For example, from A to B, right? 0 to 1 or any range. So that we can use some thresholding mechanism, we can use some threshold in between, and can convert into a binary output or multi-class output, right? So how do we solve this problem? So we have also seen the similar solution in the previous slides, that we can take a threshold, let's say zero point 0.5 in between, right? And we can simply sort of classify the points which are above zero point 0.5. For example, if you just take hours of study as 6, its prediction would be somewhere here, right? So if we go by this logic, these points would be misclassified, right? For example, this point is misclassification because this point belongs to yes class, the green space. However, it was predicted to be in the red class, right? Similarly, all of these points would be correctly classified, right? And these points are also correctly classified. And we can sort of calibrate this threshold based on the data. Like we can use some sort of calibration mechanism, right? That can give us the right threshold. All right. So let's say even if we solve the problem one by taking a threshold and calibrating it based on the uh, data, but there is a bigger problem, and the problem is that even a single outlier can pretty much break our classifier. How? Let's see this through an illustration. So let's say we have these two classes, green and red, and we have fitted a linear regression model, and we have solved our first problem, that we have taken, let's say, zero point 0.5 as a threshold. And if we take this, essentially now we have a right classifier, which is sort of classifying all these points correctly, right? So these points would be in one class, and the red point would be in another class. So far it's good, right? Now let's see what happens when we have an outlier. So this is the outlier, and when we try to fit this model now in the presence of this outlier, so in order to adjust or in order to reduce the overall cost, the outlier, or sorry, the classifier would get tilted towards this outlier, right? And now see what happens now. So on the same threshold 0 point 0.5, our decision boundary is this now, right? So essentially all of these points, right, all these right points which were correctly classified earlier, they are now misclassified, right? So this is a huge problem, that we cannot use linear regression for classification problems. So having said that the outlier is a huge problem, let's try to understand why exactly this outlier is a serious problem with linear regression. So linear regression, we have hypothesis like this, and we have cost function like this, and we have, let's say, this best fit line, passing through these points. And when we have the outlier, what happens is when we compute this distance, right? Because in case of in this cost function, we compute the difference between the actual value and the predicted value. So let's assume this distance was, let's say, 2, and assume this was, let's say, again 2, and assume, let's say, this is 1, right? And as compared to these distances, this distance would be, let's say, 20, right? So this is already a large number as compared to these distances, right? And when we look at this cost function, essentially what we are doing here is we are squaring these distances. That means this would something like 2 square, which is 4, again 4, and plus 1 square is basically 1. And then when we square this number, this 20, this would become 400, right? That means this distance would contribute heavily towards the overall cost. So now, to reduce this overall cost, the optimization algorithm will try to tilt this model towards the outlier. And that's where the problem is. So what's the takeaway? The takeaway is that this least squares is not a suitable cost function for logistic regression, right? And that's why we modify the hypothesis as well as cost function for logistic regression.